Hello, my name is Professor Adjovan, and this is episode 10 of the Quadratic series, where we're going to be talking about special cases when it comes to factoring quadratics. If you haven't watched the previous two episodes in this series, I highly recommend that you watch those first to learn all the other different ways to factor. And if you haven't watched episode 5 yet, where we talk about multiplying polynomials and their special cases, you should definitely watch that first because some of the things from that video are coming back into this one. So we're going to look at three examples in this video. If your problems that you're working on, homework problems, whatever it is, looks like these problems, and this is the correct video for you. If you are looking at these problems and you think that you already know how to do them, I would recommend going on to the next episode in this quadratic series. For everybody else, let's go ahead and jump into it. So from episode 5 in the quadratic series, we learned that a plus b squared is equal to a squared plus 2ab plus b squared, and that a minus b squared is equal to a squared minus 2ab plus b squared. So when we're factoring, we're going backwards. We're given the polynomial, meaning we're given this, and we want this. I personally think that it's difficult to identify when you are given something in this form of a squared plus or minus 2ab plus b squared. I'll give you an example. If you were told to factor 4x squared plus 12x plus 9, I'm sure most of you, myself included, would do this the way that we've done in the past couple of videos, where we look at, well, what is a times c? 4 times 9 is 36, and what are factors of 36 that are going to add to make 12, 6 and 6, and start doing this the normal way, which is perfectly fine. And in fact, it's what I recommend. However, we can identify that this, and this is an a squared, a 2ab, and a b squared. If this is a squared, then a must be equal to 2x. If this is b squared, then b must be equal to 3. Not 2, 3. If a is 2x and b is 3, does this middle term of 2ab hold up? Well, 2 times 2x times 3 is in fact 2 times 2 is 4, times 3 is 12, 12x, it works. So I know what a is, I know what b is, and it's in this top form, so I know that this factors into a plus b squared, and because a is 2x and b is 3, I know it factors into 2x plus 3 squared. But we could have done this the way that I originally wrote, where we do it with the 4 times 9 is 36, and the two factors of it, and rewriting it, and then working into factoring by grouping, and we would have gotten the same answer of 2x plus 3 times 2x plus 3, which we know it's a repeated binomial that we could write as 2x plus 3 squared. So if you don't see this, if you don't see that this is in the form of a squared plus 2ab plus b squared, you can just factor it normally and you'll end up at the same answer. So I don't recommend trying, unless you can just see it immediately that it's in this form, then it may be beneficial, but 99% of the time I would just factor this normally. There is a third special case from that episode 5 video with multiplying special cases, multiplying polynomials with special cases, that is beneficial to know to factor. So we're looking at things like x squared minus 25, where there's no b term, there's no middle term. So if we were to do this the way that we've been doing it, I would look at negative 25. What are two factors of negative 25 that add to make 0? Well, I have 1, negative 25, negative 1, positive 25, negative 5, and positive 5, which, if we add them together, we do get 0. So I could write this as x plus x squared plus 5x minus 5x minus 25. Because I have a polynomial in 4 terms, I know that I'm factoring by grouping. I can take out an x on the left, be left with an x plus 5, and I can take out a negative 5 on the right to be left with an x plus 5. These two are the same, so x plus 5 is one of my factors, and then the two things that were taken out as GCFs make the other factor. Now, if you've seen the previous video, episode 5 specifically, this should look familiar, and we called these two binomials, we called them conjugates, because they look exactly the same, but the sign between them is different. So I have an x plus 5 and an x minus 5. So what's going on here is that this is a special quadratic. This is the difference of two squares. It is the difference between a squared and b squared, which we should recall is equal to the conjugates of a plus b and a minus b. So rather than doing factoring the normal way that we do it, we can see that there is an a squared and a b squared, identify what a and b are, and then write it as the product of the two conjugates. Let's look at that with another example. When I see a quadratic without a b term, the first thing I'm doing is looking at the a x squared and the c term, and I'm identifying, is this a perfect square? 9 is in fact a perfect square. X squared is definitely a perfect square, so this could be an a squared. 49 is a perfect square, so this could be a b squared. If this is a squared, then a must be equal to 3x. If this is b squared, then b must be equal to 7. Because I know my a and my b, I know that the two factors of this are a plus b and a minus b, meaning 3x plus 7 and 3x minus 7. So we factored this quadratic without even factoring, because we know the difference between two squares. So this is one of the 3 special cases that we've previously talked about, and it's the one that I highly recommend that you identify and use to make your factoring quicker. We have one more example. I have an 8x squared minus a 32. But if I look at 8x squared, if I look at negative 32, these are not perfect squares. Perfect squares are 1, 4, 9, 16, 25, etc. 8 is not a perfect square. 32 is not a perfect square. So I could try to factor this using the AC method with 8 times negative 32, but those numbers are going to get very big very quickly, and we don't want to deal with that. So from the last video, I recommended that the first thing you do, especially when you see a times c is giving you a large number, is trying to factor out a greatest common factor in the very beginning. Is there a greatest common factor between 8 and 32? Well, yes, there's 4. So if I factor a 4 out, I'm left with 2x squared minus 8. Is 2 a perfect square? Is 8 a perfect square? No. So factoring out a greatest common factor did not get us anywhere. Interesting. Is there something I can factor out that would turn this into a perfect square in both of these terms? They only share one other factor in common, and that's 2. If I take a 2 out, I'm left with a 4x squared minus 16. Well, 4 is a perfect square, and 16 is also a perfect square. So if this is an a squared and this is a b squared, then my a must be equal to 2x, and my b must be equal to 4. So we factored something out from our original quadratic to make this be in the form of a squared minus b squared. Now that I've identified what a and b are, we can rewrite this as a plus b, or 2x plus 4, times a minus b, or 2x minus 4, and we can take the number that we pulled out, in this case 2, that also needs to come down and be in front because that's one of the factors. This was the last video where we are discussing factoring. In the next video, we're going to start talking about an application of factoring, or solving quadratics. If you found this video helpful, consider giving it a like and consider subscribing for more math lessons. If you have a question related to this video, comment it down below and I'll do my best to answer. If you have a suggestion for some sort of math content or math lesson that you would like me to cover specifically, go ahead and comment that down below too, and I'll see if I can get to it. Thanks, and I'll see you in the next episode.